Welcome back. In the previous video, we had seen that all models, all linear models can be written in the form x w time equals y hat, where this x was called the design matrix and consists of all the input vectors, okay, or all the input variables. The size of this is the number of examples or the number of sensors that you have multiplied by the number of features with which you wish to represent it, okay, where m is the number of data points and n is the number of features. And I had explained features the last time. For example, if you have x itself, the input variable could be made up of multiple components. For example, it could be made up of the x location and y location of a specific point. More generally, it could be other things also for any linear regression problem. For example, let's say you're trying to make weather prediction and you could have pressure and temperature as two components, or pressure, temperature, humidity in case you have three features, so on and so forth. W is the parameter vector, and W is made up of n+1 components. This in machine learning language is called the bias unit. And X, if you remember, is also augmented by a bunch of ones so as to multiply this. And this, of course, is our model. So this problem is, or this model is linear in W. That's the important point. It is linear in parameter space. It doesn't have to be linear in X. Okay. So X itself could contain, as we saw in the last video, it could contain X square. It could contain sine X. It could contain cosine X. It really doesn't matter because this is constant. It depends on data that we have given. And W itself is the parameter vector. And it's the parameter vector which is the unknown which we are trying to solve for. We also saw that if we take this matrix formulation, we can now write the objective function as J, the objective function, is equal to W transpose X times W. This is a quadratic term. It's quadratic in X, or it's quadratic in W, sorry. These two are linear terms in W, and this is constant. Okay. And as I talked about last time, to find the minimum of J, we need to minimize with respect to the variable. The variable here is not the data points. We can't change the location of the sensors, the location of the thermocouples, or what value they have measured, but we can minimize with respect to the parameter, with respect to W, which means we are minimizing with respect to these n+1 variables in general. Okay. Now, how do we minimize? So we minimize in the following way. We say del J del W naught equal to 0, del J del W1 equal to 0, so on and so forth, up until del J del Wn equal to 0. Now, this can again, okay, in the same notation, this can again be written in a form which looks like a vector. So it can be written in the form, the vector or the matrix form is we say del J del W equal to 0. Now notice J is a scalar, but W is a vector, okay, n+1 cross 1 vector or a matrix. Okay, so this is the same as saying del J del W can be written as del J del W naught, del J del W1. So this is the definition of del J del W. So it is this that we use in order to So it is this that we use in order to actually set the equation. So we will say del J del W equal to 0. This has the same meaning as the scalar system of equations. Here del J del W is a n plus 1 cross 1 vector, and 0 also actually is a bunch of zeros. It's n plus 1 cross 1. So I am going to start with this equation, which is del J del W equal to 0. Okay. So we have this equation, let's call this equation star, and we have this original equation, let's call this equation 1. Okay. So basically what it means is we need to find out del J del W. Now if we look at this, it is made up of 3 terms, the quadratic term, 2 linear terms. Of course, del J del W with respect to a constant is 0. Okay. Now, the way we are going to do it is first we will do the linear terms, then we will do the quadratic term. This is going to involve some amount of matrix algebra. I hope you can follow it. Even if you can't really follow it, though I do have a couple of questions with this in the exercise, you should be able to understand the overall sense. At least the linear terms are fairly easy to calculate. So I hope it's a useful skill that you learn, even though that's not the main point of this course. Okay, so let's now differentiate these terms. Okay, so now consider terms of 2 forms. Okay, so I am going to say some matrix E1 is, let's say, C times W, and where C is a matrix and W is a matrix. Okay, so for example, C could be C1, C2, Cn, and W could be W1, W2, Wn. It doesn't matter whether we start with 1 or n, I am just trying to derive a general result. Okay, so suppose I want dE1 or del E1 del W, okay, which is the same as, okay, instead of calling it E1, maybe a better name would be simply E. Okay, just so that there is no confusion, I'm going to call it E. So del E del W1, by our definition, del E del W2, we are going to differentiate with respect to each one of the components. So all we need to find out is E is now a scalar. Remember, E is a scalar, C is a vector, W is also a vector, but C is a 1 cross n vector or 1 cross n matrix, and W is a n cross 1 matrix. So E is actually a scalar which is equal to C1W1 plus C2W2 up until Cn/Wn. Okay. So now if we see this and we try to find out what del E del W1 is, del E del W1, all other variables are 0, and the only term that remains is C1. Del E del W2 is C2, so on and so forth, and del E del Wn is Cn. Okay, so this is the result of del E del W. What is this? If C is the row matrix, this then is C transpose. I think that should be clear. So let's summarize the result. If you have a matrix or if you have a scalar which is E equal to some C times W, this means that del E del W is equal to C transpose. Okay, so let's label this result as 3. Okay, now I am going to write another case. Similarly, consider another case. Okay, so the other case is D equal to W transpose times D. Okay, Now what is B? B I am going to write as B1, B2, Bn. So B is a n cross 1. W transpose, of course, is W1 capital Wn, which means del D del W is del D del W1 del D del W2, sorry, del D del Wn, and D is nothing but, you can now write it out, W transpose times B, so which is W1 B1 plus W2 B2 until Wn Bn. Okay, so which means del D del W you can now write as, differentiate with respect to W1, it is simply B1, B2, so on and so forth until Bn. Okay, so this tells you this is exactly the same as the original matrix B. Okay, so this tells you that if D is equal to W transpose times B, then del D del W is simply equal to B. Okay, so let's call this equation, the previous equation was 3, this equation as 4. Okay. Okay, so now we are going to use 3 and 4 to solve for the linear derivatives. Okay, so the linear derivatives are the derivatives here, these two. So let's look at the derivative of these two terms. So the first term I'm going to look at is this term here, W transpose X transpose Y. Okay. So let E equal to W transpose X transpose Y. Okay. I want del E del W. I think I called it D here. So let me keep consistent notation. So let this be D. And let's call this term B now. This is W transpose B. So we know that del D del W is B, which is nothing but X transpose Y. Okay. So del D del W equal to X transpose Y. So this result directly leads here. Okay. So similarly, the other term we had was the term here. This term here, which is Y transpose X W. Okay, so let's call that E. Y transpose X W BE. We want del E del W. We had the result before. Let's call this C. So del E del W, when this is CW, is something we already know. This is C transpose. So this means del E del W is Y transpose X transpose, which, as you know, AB transpose is B transpose A transpose. So this becomes X transpose Y again. Now notice both these terms are the same. Okay. So this you should know with solving quadratics. For example, if you have something like x square, you tend to get 2x when you take a differentiation. So something similar is going on here, but we'll go further. Okay, so now what we get is, finally, let us look at the quadratic term. Okay. This I'm going to do a little bit of hand waving. I will not do it in as much detail as the previous terms. I'm going to appeal a little bit to your knowledge of scalar calculus or one-dimensional calculus and not vector or matrix calculus. So the quadratic term here is, if you go back here, it is x transpose w transpose x transpose x w. Okay, so I'm going to call this quadratic term is w transpose x transpose x w. Okay, so let's call this term as A. Okay, so that is w transpose AW. Okay, now let's say F equal to w transpose A times W. We want del F del W. The way we will do it is using something like the chain rule. So you know that the chain rule works this way. If you have, let's say, d by dx of f of x multiplied by g of x, the way we do it is we first differentiate this assuming g is constant, then we differentiate it assuming f is constant, and then add the two. So we will say something like df dx multiplied by g of x plus f of x dg dx. Okay, so the idea is differentiate this whole term assuming g is constant, then differentiate this whole term assuming f is constant, then add the two. Okay, we are going to do the same thing here. So we are going to treat it in the following way. We will differentiate this whole term holding this term constant, then they will differentiate this whole term assuming this term is constant, and we will just write a sum of the two. So for example, I am going to call this combination, let me be consistent with my notation here. I'll call this term as C and this term as B. Okay, so if I do that, this basically becomes del by del W of C times W plus del by del W of W transpose times B. Okay. Now we know the result already when you do that. So when you do this, you get what is derivative of C times W? We already calculated it. This is C transpose. And what's derivative of W transpose B? We know that that's B. Okay. Now C was W transpose A. If you take transpose of that, you get A transpose W, and B is simply AW. Okay. So put these together, you get del F del W is A plus A transpose multiplied by W. Okay. Now A itself was XX transpose, or sorry, X transpose X. I think that is the definition. Yes. So X transpose X. But X transpose X, if you take a transpose of that, you will again get X transpose X. Okay. That's because it's symmetric. So you get 2 times X transpose X W. Okay. So this means derivative of W transpose X W is 2 X transpose X W. So again, like I said, this is kind of a hand-waving derivation. You can do a more formal derivation, but nonetheless, none of what I said here was strictly speaking wrong in any way. All you need to remember again is to treat, if you treat this as a scalar, let's assume W is a scalar, then it will look like d by dw of X transpose X multiplied by W square, which will simply be 2 times X transpose X times W. So it works in a scalar, and matrix, you have to be a little bit careful in order to ensure that all the matrices match. So all put together, okay, if we now sum all terms together, you'll get del J del W. Now you will notice this half actually is very useful for us, this half up front. You will get a 2 from the differentiation of this term. You will also get a 2 from the sum of the differentiations of these terms. So just look at the results once. You have this 2 times x transpose xw. You also have an x transpose y and another x transpose y from here. Okay. So when you add all that, so you will get half times, there will be a 2, then x transpose xw minus x transpose y. Okay. If this is not entirely clear on how this came, I request you to just go back and look at each individual term. So these 2's of course cancel out, and this is equal to 0. So this tells us that x transpose xw is equal to x transpose y. Okay. This set of equations are called the normal equations. So these are called the normal equations, and these are exactly the same equations that you would get with the scalar approach. That is the approach with which we derived our x bar formula, etc., on the last time. That is exactly what you would get with this approach also, except it is compact and it is one general formula for every single type of model, true for every linear model. A few other things about this model I would like to say here. The first is this, that let's take the case of a simple linear model which we did. Okay, so the linear model that we had was y hat at any point is this w0 plus w1 plus x at that point. So if we look at the design matrix capital X in this case, this is going to be 1 x1, 1 x at the second point, and 1 x at the mth thermocouple location. Look at the size of x. X is an m cross 2 matrix. What is x transpose? X transpose is, of course, the transpose of this matrix 1, 1, 1, x1, x2, xm. Okay. Now, suppose we want x transpose x. Okay, so this, of course, x transpose is a 2 cross m matrix. So 2 cross m multiplied by m cross 2 is going to be some 2 cross 2 matrix. Okay. Now, what is that? So let's see, x transpose, the first row into first column, it is just a bunch of ones. I'm going to write it as 1 plus 1 plus 1. Of course, it's just sigma 1 from I equal to 1 to m. This is going to be m, but I'll leave it as sigma 1. Okay. Next, this location will be first row into second column. You can see 1 into x1 plus 1 into x2. So this is simply sigma x or sigma xi. It's symmetric. So this one is also going to be sigma xi. The final one is x1 square plus x2 square up till xm square. So this is sigma xi square. Okay. Now the equation was x transpose xw is equal to x transpose y. Okay. So this is the x transpose x w. Now we next have to do x transpose times y. Y we already saw is simply y1, y2 up until ym. Now what is x transpose y? It has to be a 2 cross 1 matrix. first row into first column is simply sigma y. And second row into first column is x1 y1 plus x2 y2. So this is sigma xi yi. Okay. Now notice what has happened. This is the x transpose x matrix. And all you got was a 2 cross 2. You summed up across all these things and you got a 2 cross 2. In case of a quadratic, this will become a 3 cross 3. Now notice, if you go back to your notes from the last week, this is exactly the same as before. Okay. So this way is just a compact way. Compact way means it will look like a long way, but it's compact way in the sense that you can do this one equation, one normal equation derivation for every single case on earth for linear regression. So this also is exactly the same as before. So notice this. So in general, you are going to have an n plus 1 cross n plus 1 if you have n features. Okay, so in this case, this is a 2 cross 2 matrix. Now, another thing about this is X itself has an interpretation which we will use later on when we move to nonlinear regression. Okay, so let's take the X matrix. I'm going to write this again. It's 1, x1, 1, x2, and up till 1, xm. Y hat, as you know, was w0 plus w1 x1. This is our model. w0 plus w1 x2, w0 plus w1 xm. This is w1. Should not look like w2. Okay. Now, if you look at the relationship between the y hat and x, it's not immediately obvious, but if you stare at it for a little bit longer, you notice this, that the first term here, okay, 1 is nothing but del y hat 1 del w naught. How am I saying this? Notice this. This is y hat 1. So if I differentiate this term with respect to w naught, I get 1. Of course, if I differentiate this term with respect to y hat 2, with respect to w naught, I get 1, 2. So I am going to write it this way. The first term is del y hat 1 del w naught. The second term is del y hat 2 del w naught. And the last term is del y hat m del w naught. The next term here, the next column, this column, you can now notice is x1 is nothing but the derivative of the first term with respect to del w1. You notice the w1 coefficient is x1. So this is del y hat 1 with respect to del w1. Similarly, del y hat 2 with respect to del w1. And the last term is del y hat m with respect to del w1. Overall, at least in this case, we saw that del y hat del w with a little bit of abuse of notation, this kind of this Jacobian. You should have a few transposes here, but we are going to, this equals x. Okay. It looks at least like x. Whether you want to write it as del y hat del w, we can debate. But you can see that the differentiation of the y hat vector with respect to the w vector is related to the x vector. So these quantities have physical meanings, and these are called sensitivities. And we will use them, and we are also going to use them for nonlinear extensions in the next week. Okay, the final point, when we solve for w, so remember the equation is x transpose x w is equal to x transpose y. The way we solve for W is, of course, we can write the equation. W is X transpose X inverted X transpose Y. So generally not a good idea to invert. Okay. In practice, we use Gauss elimination, etc. There are other methods too, but my point is you should not build the matrix and kind of invert it. That's generally not such a great idea. Okay. We will also look at alternative iterative methods later on. I'll also show you a code later on this week. Using partially this idea, I'm going to use some internal routines in MATLAB to do this. Okay, so within this video, we did a derivation of this. Some people call this also the normal equation, but it's preferable to call this equation the normal equation. But either way, you take this gigantic matrix, as long as you have a linear model, you can always come up with this. There are some other interesting things that are going on here, which I'll come to when we come to the nonlinear models. Now, later on this week, we are going to move on to certain variants, and where all this one simple model is useful, you will see that in the future videos. Thank you.